This lecture deals with LR parsers. So LR parsers are basically bottom-up parsers that scans the input string from left to right and generates the rightmost derivation in reverse order. So that is the reason for calling this type of parsers as LR parsers. It scans the input from left to right. So this L stands for scanning the input from left to right, and it actually generates rightmost derivation in reverse. So this R stands for rightmost derivation. So LR parser actually scans the input string from left to right and generates rightmost derivation in reverse order, and that's the reason for calling this parser as LR parser. Now let us discuss the general structure of an LR parser. So this figure shows the general structure of an LR parser. There are main two components, a driver routine and a parsing table. So the driver routine is the program that performs the parsing operation, and in order to proceed parsing it needs a table, that is a parsing table, which contains some information that helps the driver routine or the parser program to decide whether to perform a shift operation or whether to perform a reduction operation or whether to accept the string or whether to report an error. So it will receive the input string, and the driver routine, depending upon the parsing table, verifies whether the string is valid or not, and depending upon that it will generate the output. It will either accept the string or it will generate an error. The string is invalid. Now there are, depending upon the way in which you are generating the parsing table, you can have different type of LR parsers. So one classification is simple LR parser, termed as SLR, and this or the parsing table corresponding to SLR parser can be easily generated. So you can easily design or construct the parsing table corresponding to simple LR parser. So it is easy to design the parsing table, but it is actually less powerful in the sense, for all context-free grammars, you cannot generate an SLR, simple LR parsing table. So this SLR parsing table can be constructed for a small class of context-free grammars. So this can be used to parse a small class of programming languages, a part of languages. So that is the restriction for simple LR. That is the reason for calling it as less powerful. But you can easily construct the parsing table. Now the second one is canonical LR parser. So that is termed as CLR, canonical LR. So it is pretty difficult to design the parsing table. As compared to remaining LR parsers, but it is very powerful or most powerful. Most powerful in the sense for almost all class of language you can have or construct a canonical LR parser, or the class of programming languages very big as compared to the other categories. And the next one is look ahead LR. So this is termed as LA LR parser. So if we consider the difficulty in designing the parsing table for LA LR, it actually lies in between this simple LR and canonical LR. It's again difficult to design the parsing table, but the power actually lies between SLR and CLR. So if we consider the difficulty in design, it is difficult to design LALR as compared to simple LR, but little bit easy to design LALR as compared to CLR. But if you consider the power lies between SLR and CLR. LALR is powerful than SLR, but it's not that much powerful as compared to canonical LR. So depending upon the parsing table, you can call parsers SLR parser or canonical LR parser, CLR parser or LALR parser. So let me move on to a sample parsing table. So for all LR parsers, the driver routine will remain same and the parsing table will change. So if you want to design an LR parser, you can either design SLR, CLR or LALR depending upon the type of the grammar. For all grammars you cannot design SLR parser. So if you are inserting the parsing table corresponding to SLR into the LR parser, then that parser will turn to SLR parser. Or if the parsing table use this LALR, then you can call that parser as LALR parser. So this is the general structure of a parsing table corresponding to this grammar. So parsing table mainly consists of two parts. One is the action part and another one is the go-to part. So parser actually performs any one of the four actions. So it will either perform a shift operation, or it will perform a reduce operation by applying some production A giving alpha, or it will perform or it will accept the string, that is another operation, and the fourth one is error. So these are the four actions performed by LR parser, and if you consider the action part of this parsing table, LR parsing table, you can see that some entries are actually blank. These blank entries represent error. At some point, if you refer to, or the driver routine refers to this blank entry, then that will lead to an error. So it will report error at that time. So depending upon the row and depending upon the column, if it moves to a blank entry, then at that time the driver routine will report an error. And again, in this case, if the driver routine access this particular location, if it access accept, then that string will be considered as a valid string or syntactically correct string. And if it access this particular location, this S actually stands for a shift operation. S represents shift. So it will perform the shift operation of the current input into the stack along with the corresponding state. So S stands for the shift operation and 3 actually represent the state. So if the driver routine refers to the location 0 ID which contains S3, it actually at that point this parser will perform shift operation of the current scanned input into stack, followed by shifting the state label 3 into stack. Now, so we have discussed accept, shift. Next one is reduce operation. Here R actually represent reduce. These are actually reduce operations. So whenever the parser access the location containing reduce, it will apply a reduction operation by performing the corresponding production. For example, if it accesses R3, then it will perform reduction by applying the production number 3. So we have labeled the production using numeral 1, 2 and 3. If the driver routine or the parser program accesses this location, then it represents reduction using production number 1. So that is what I meant by action part. Next one is go to. So go to is another function performed by the parser. So if the current state is 0 and immediate to that state, if the element in the stack is E, so assume that 0 is there in the stack, and after reduction we have performed push operation of E into stack, then it will perform go to operation. Go to 0E. Go to 0E is 1. So that 1 will be pushed into stack. I will try to make it clear by considering a simple example. So this parser actually uses a stack to proceed parsing operation. And if we consider stack content at a time, it will be of the form S0, X0, S1, X1, S2, X2, X1, X2, S2, X3, S3, etc. up to Xm, Sm. So this will be the string in the stack at any particular instant. Here each Si represents the state. So S0 is a state, S1 is a state. At any point stack top will be a state. And X1, X2, etc. Xm actually represent grammar symbols. It could be terminals or non-terminals. So at any point some state Sm will be there in the top of stack. So you are having the string from S0 to Sm in the stack. At some point, at any particular instant, a state will be there in the stack which represent or holds the complete information regarding the string that is there in the stack. So this state information actually helps the parser or driver program to take a decision. Now, let us consider a string that is derivable from this grammar. Let it be id plus id dollar. So you are having stack, you are having the input to be scanned, and next one is the action. So initially stack contains the starting state 0. So you assume that 0 is the starting state, and the input to be scanned is id plus id dollar, and dollar will act as the right hand side delimiting symbol for the input string. Now it will check the stack top. Stack top is 0 and the input is id. So it will go to the location. The driver program or the parser program will check the location 0 id. So at each and every step it will take the pair that belongs to the stack and the input. So 0 id. So 0 id actually represents S3. S3 stands for shift operation. So this actually represents a shift operation. Action performed is shift. So the current symbol ID will be shifted into the stack, pushed into stack, followed by shifting the state. State is 3. So 3 will be shifted. So remaining string to be consumed is plus ID dollar. Next configuration is 3 plus. So it will check the parsing table, row corresponding to 3 and column corresponding to plus. So this actually represent the stack content and this represent the input symbol. So 3 plus actually represent R3. So you are expected to perform a reduction operation by applying the third production. So third production is T giving ID. So what happens is it will perform a sequence of push operation, a number of push operations which will be equal to double the length of right hand side of this production. So if you consider length of right hand side, it is 1. You are having only one terminal symbol. So it will perform 2 pop operations. So first popped element will be, so if you consider the stack, it is expected to remove first 2 symbols from the top. So 3 get popped and ID get popped. So remaining content will be 0. And the left hand side will be pushed into stack. So T will be pushed into stack. So once more I will repeat. Here you are going to perform a reduction operation, T giving ID. So it will perform that number of pop operations which will be equal to twice length of right hand side of the current production that you are going to apply. So here length of this right hand side is 1. So you are expected to perform 2 pop operations. So 3 get popped and ID get popped, and the left hand side T will be pushed into stack. So whenever you perform a reduction operation, you are expected to, or the parser will perform a go to operation. So go to 0T. 0T is 2. So 2 will be pushed. So always the state label will be there in the stack top. So if we, before performing this go to operation, a grammar symbol is there in the stack top. So in order to maintain that property, you have to perform a go to operations, go to 0T, which is 2, and that 2 will be pushed into stack. So the remaining input is plus ID dollar. Next configuration is 2 plus. So 2 plus, here it is S4, that represent shift operation. So 0T2, the current symbol plus will be shifted along with the state numeral. You are performing S4, so current symbol plus will be shifted into stack, followed by pushing 4 into stack. So the remaining input is ID plus ID dollar. Next configuration is 4ID. So it will check 4ID. 4ID is again a shift operation. So 0T2 plus 4ID. So while performing shift operation of ID into stack, it will perform push operation of 3 because the current shift is labeled S3. So 3 will be shifted. Remaining input is plus ID dollar. Next configuration is 3 plus. So it will check location corresponding to 3 plus. 3 plus actually contains R3. So you have to perform a reduction, reduce by applying production number 3. So T giving ID. As I said, the right hand side is of length 1. So it will remove 2 items from the stack top. So that is actually the handle. So this state actually holds the information regarding the handle currently present in the stack. So the handle is ID and that is right delimited with 3. So this ID 3 get popped from the stack. So the stack will be 0T2 plus 4. During the reduction operation, this ID 3 get removed and the left hand side of the production, that is T, get pushed into stack. So as I said, when we perform a reduction operation, you have to execute go to. So what is 4T? 4T is 2. So 2 will be pushed. Now the remaining string is plus ID dollar. What is the next configuration? 2 plus. It will verify 2 plus. 2 plus is actually a shift operation. Shift operation. So 0T2 plus 4T2 plus. So 2 plus is actually shift operation of 4. So plus will be shifted and 4 will be pushed into stack. And the remaining input is ID dollar. So what about next configuration? Next configuration is 4ID. 4ID is again a shift operation. That is shift operation of state 3 into stack. So the content in stack will be 0T2 plus 4T2 plus 4. ID will be pushed into stack, followed by shifting 3 into stack, and the remaining input is dollar. Next configuration is $3. So it will check the location $3. That is a reduce operation. Reduce by applying third production, T giving ID. So it will perform pop operation of this string. This is the handle. Pop from the stack. So 0T2 plus 4T2 plus 4. This get popped, and the left hand side of the production T get pushed into stack. Since it performs a reduction operation, it will apply go to. What is go to? 4T. Go to 4T. 4T is actually 2. So that 2 will be pushed. Next configuration is $2. So $2 is reduction. Reduce by applying $2. Reduce by applying second production. That is E giving T. So since right hand side is of length 1, string of length 2 get popped from the stack. So you will be getting 0T2 plus 4T2 plus 4. This T2 get popped from the stack, and the left hand side E get pushed into stack. Since we have performed reduction operation, we have to execute go to. What is go to? 4E. 4E. Go to is 5. So 5 get pushed. Remaining input is dollar. Next configuration is $5. So what is $5? You have to perform a reduction. Reduce by applying first production. So that is E giving T plus E. So here length of right hand side is 1, 2, 3. So you are expected to perform 6 pop operations. So 1, 2, 3, 4, 5, 6. So the configuration $5, that is the state 5 actually holds information regarding the handle in the stack top. So this content get popped from the stack. So let me continue at this point. And the remaining stack content will be 0T2 plus 4. This content get popped, and the left hand side of the production E get pushed into stack. Since we have performed a reduction operation, you have to execute go to, that is go to 4E. Go to 4E is 5. So 5 get pushed. And as you all know, the remaining string is dollar. What is the next configuration? That is $5. So if you consider $5, the operation is reduced by applying the production E giving T plus E. So it will perform 6 pop operations, 1, 2, 3, 4, 5, 6. So this will be the handle, and that will be popped. and that will be replaced with left hand side of the production. So E get pushed. Since we have performed a reduction, apply go to 0E. 0E is 1 and the stack content is $. Next configuration is $1. So it will check the parsing table, $1. So the entry is accept. At this point the string is said to be accepted, or the parser will generate accept as output. So this is the working of a typical LR parser. Now let me define LR grammar. What do you mean by LR grammar? So if it is possible to construct a parsing table with unique entry at each location, then we can call that grammar as LR grammar. A grammar is said to be, a CFG is said to be LR if the parsing table constructed is having, parsing table corresponding to that grammar constructed is having unique entry. So assume that this parsing table is having multiple entry, S4, let it be R2 here. So S4, R2. So if you are having two entries in a particular location, then you cannot call this grammar as LR because this entry is not unique. So this actually leads to a shift reduce conflict, that is from state 2 and for the input and for input plus, you can either perform shift operation of plus into stack, or you can either perform reduction by applying second production, that is actually shift reduce conflict. Again you can have multiple entry like this, R3 and R2, that is from current state 3 and the input plus, you can either perform reduction using the second production, or you can either perform reduction using the third production. So you are having reduce conflict. The first one that I have mentioned is shift reduce conflict, either perform a shift operation or a reduction operation, and the second one is reduce conflict. You can perform multiple reductions for a particular configuration. So if the parsing table generated is having unique entries, then you can call that grammar as LR grammar. Now generally you can have LRK grammar. So what do you mean by LRK grammar? So the grammar that can be parsed using LR parser by looking ahead K symbols, K input symbols at each move. So in the previous example we have considered parser that proceeds by looking one symbol ahead, or currently it will verify one symbol and take a decision. So if the parser proceeds by examining up to K symbols ahead, then you can call that parser as LR. Then you can call that parser as LRK parser, and the corresponding grammar is called as LRK grammar. Then what do you mean by LR1 grammar? That is the LR parser that parse the grammar by looking one symbol ahead. That is what you mean by LR1 parser. Now, how will you define non-LR1 grammar? So, a grammar is said to be non-LR1 grammar if every shift reduce parser constructed for that grammar will reach some configuration that either leads to shift reduce conflict or reduce conflict. That is, if we construct any LR parser for this particular grammar, then at some point the parser will reach a configuration from where it cannot proceed further. So such grammars are said to be non-LR1 grammar. So you can consider a simple example for non-LR grammar. For example, let this be the grammar, yes, giving if condition then statement, or if condition then statement else statement, that contains dangling else. So if we consider this grammar is actually not an LR grammar, and again because the main reason is that this grammar is basically ambiguous grammar. So no ambiguous grammar is LR. So if you are having an ambiguous grammar, you can conclude that that grammar is not LR. Again, if you are given an unambiguous grammar, that grammar could be either LR or non-LR. That's it.